Recording. So let's take a look at the first one. And it says, a billionaire hires you to mow her lawn. For pay, she'll give you a penny for the first job and then double your pay each time you complete a job. Anybody taking that job, by the way? No, me neither. Okay. Some of y'all would take it?
Yeah.
Okay. Why would you take it?
At some point, I'd be a billionaire.
You would be. All right. So to start out, it's not going to get there very quickly, but it is going to double every time. So let's see what will we get. How much money could you expect on the third job? 4 cents. Okay, 4 cents. On the first job, we'd make 1 cent. On the second job, we'd make 2. On the third job, we'd make 4. Okay, so let's write a rule that would give us how much money we would make on the nth job. All right, on that nth job. So let's see. Let's just call it P of N.
Yeah.
Okay. Is it exponential? Yeah. Yep. Okay. We start on the first job with 1. It's going to double each time. What should my exponent be?
0.1 n.
N minus 1. All right. N minus 1 because it's our first term. Okay. And this should be 0.01, right? Okay. Yeah. Sorry. So 0.01 times 2 to the n minus 1. On our first job, we make 1 cent. So my exponent has to be n minus 1. We don't have the 0th job, okay? If we had the 0th job, we would have to do what to that 0.01? Yeah, it'd be 0.005. We have to divide it in half, and then my exponent could just be n, okay? All right, so let's look at the next one. It says identify whether the following scenarios would represent exponential growth, exponential decay, or neither. And let's just give a reason, just thinking. We buy a car that loses 20% of its value each year. What do you think? That is exponential decay. All right, the reason why? We multiply by what percent every year? If I'm losing 20%, how much am I keeping? 80. We multiply by 0.8 each year. That's how much of the value of the car we're going to keep. All right, we're going to lose 20 but keep 0.8. Right? On the next one, a restaurant job shares 3% of its total sales for each shift with its employees. What do you think? It's going to be neither. Are we going to have a constant proportional rate that we're going to get every time? No. Okay, this one's going to be neither. All right. The battery life on your phone decreases by 10% every hour. Oh, tricky, tricky. All right, this one's a little bit tricky. This one's actually linear. Okay. Yeah, because we're losing that 10% each hour. So my battery doesn't decay exponentially. It decays 10% a set amount, a constant amount each hour. Okay, so this one is actually neither because it's linear. That one's tricky. Okay, and then what about you deposit your money into an account that pays 4% interest each quarter? That is definitely exponential growth. Okay. Why is it? Well, it's compound interest. It's the #1 application for exponential functions. Okay, so good. Just kind of bringing our brain back around exponential functions and what they do and all the good things. All right. So if you notice, we've got 4 learning targets today. They'll hopefully go pretty quickly and look familiar to you as we get through there. There's probably one thing I'm going to show you that looks a little different from anything you've seen, but that's it. And we'll do several calculator problems on that last page. Okay, so we're going to talk about key characteristics of exponential functions, rewriting them in equivalent forms. AP is really big on that, seeing things different ways that are equivalent. Construct a model for situations, so that's going to be your application problems, and then applying exponential models to answer questions. Again, application-based problems. Okay, so let's just get into the basic math of an exponential function, the key characteristics, what it does, how it does it. Okay, general form of an exponential function. Y equals A times B to the X. Okay, that is the general form of an exponential function. All right, there are a couple of things that have to be true. All right, B we refer to as the base has to be greater than 0. Okay. A and B have to be constants. Okay, they're numbers. All right. A cannot equal 0. What would happen if A was 0? Yeah, I wouldn't even have an exponential function. Okay. And B can't be 1. Why could the base not be 1? Yeah, it'd just be 1 all the time, right? 1 to any power is just 1. All right, so that's why we have those requirements in there in terms of the values of the constants. We say that A represents our initial amount. Okay, it's our initial amount. And B represents that common ratio. We would probably call it the base. Okay, how do we know when we're going to have exponential growth if I'm just looking at an equation? B is greater than 1. It goes up from left to right. Okay, all of those are acceptable answers. Okay, looks something like that. A also has to be greater than 0. Okay, so to have exponential growth. Okay. Exponential decay. Yeah, it's going to go down from left to right, so the picture's going to look the opposite direction. Bless you.
Thank you.
Okay. Again, A still has to be greater than 0. Right? What about your base? It's got to be less than 1, but also greater than 0. Okay, so it's got to be like a fraction. Okay, that's between 0 and 1, or a decimal, something like that. Okay. Now, there are times when A is positive or negative, right? And we get reflections and all that kind of stuff, right? So it changes how we would say some things, but that is beyond what AP expects you to do, okay? So they're not going to question you about growth in a negative direction, all right? And that's how you would say it. So if we had a function like the top one, and it had a negative in front, let's say A was negative, it flipped it upside down, okay? That would be decay in a positive direction, which is weird, right? So, but we don't have to address that, which is nice, okay? So, yay! All right, so increasing and decreasing. When you look at these two options for your exponential function, what's the first one always doing? Under growth. Is it increasing or decreasing? It's increasing. What is your exponential decay function always doing? Decreasing. So it's either all in one or the other. Okay, so it's either always increasing or always decreasing. Okay, there are no extrema. Right? It's always doing the same thing. So if you're asked, where does it increase, where does it decrease, it's only going to do one of the two things, all right? And it would be the whole domain, all right? Likewise, when we think about concavity, okay, it's either always concave up or it's always concave down. It's neither of that switching like we've had with our polynomial functions. Which means there is no point of inflection. Dr. Pepper? Yes. Okay. Okay. So exponential functions do something that's a little different from everybody else. Now, let's talk about end behavior for a second. Okay. When we talk about end behavior, the x's are always either you're gonna go small or really big. Okay. So as the inputs increase or decrease without bound, okay, meaning they go forever to infinity. okay? The outputs do a couple of things, okay? So if we think about our y values in that exponential growth function that I drew up there, okay? As I go to, y'all are flat out allergic to pre-cal today. Like, I don't know what has happened, but y'all are allergic. Okay, I mean, we need to put Benadryl in the water. I don't know. Okay, anyway, God bless. All right. If my dog was here, he would be losing his mind. Like, if you sneeze around my three-legged dog, he tries to bite your face. Maverick. Yeah, he had a rough night last night. We haven't slept. Yeah. Okay, so let's look at the exponential growth function. As x gets towards negative infinity, what does that graph seem to get closer and closer to? Yes, on this exponential growth function, as x gets closer to negative infinity, what's the y values doing? What's the graph doing? Yeah, it's getting closer to zero, too. That's horizontal asymptote, okay? All exponential functions have a horizontal asymptote. So the outputs are going to do this, okay? We'll either approach a horizontal asymptote, okay? Or on the other side, what is that graph approaching? Infinity. If that graph was turned upside down, what would it approach? Negative infinity, okay? So we've got three things that could happen with the end behavior, okay? So it's always going to be the limit as x approaches positive and negative infinity. But depending on the graph, it's either going to get close to the asymptote, it's going to approach infinity, or if it's turned down, it's going to approach negative infinity, okay? So that's our options. Right? So when we think about the limit statements, they could look something like this, okay? The limit as x approaches positive or negative infinity of the function is either going to equal the horizontal asymptote. It might not always be zero, okay? If we move our function around, which we're going to do in a second, that horizontal asymptote's going to move, all right? If we do the limit statement, and you'd have to do them separate, okay? I'm just giving you some options. It could happen either way. It could be positive infinity, or it could be negative infinity. You really just kind of have to think about the behavior of the graph, all right? So when we write our two limit statements, we'll always write two. One is going to be the horizontal asymptote. The other one is going to be positive or negative infinity, just depending on the picture. Okay, does that make sense? It only does a couple of things. Right? It only does a couple of things. And why put that random comma right there, I don't know. Just for fun. Okay. All right. So there's all the general information about exponential functions. Okay? Let's put them to work. All right, let's put it to work. So we're going to start by doing some transformations. All right, taking a graph and moving it around a little bit. My eye's starting to twitch. All right. Yeah, it's a gift.
Then it happens.
No, it happens when I'm irritated. Okay.
I'm very sorry.
I'm about to pass out cough drops
I'm gonna get a
that are illegal. I'll have to go to jail. Okay. And I don't look good in horizontal stripes. All right, so let's look at this one. So here's my function, y equals 2 to the x. Okay? They've got some basic points there. You could jot them down if you wanted to. At 0, we'd have 1 because 2 to the 0 is 1. If we had 1, 2, 2, 4. Okay, so if you just needed some points because it makes you feel better, all right, there are a few. All right. Got it. Now, let's talk about the second one. We're going to do some translations, transformations. How is that exponential function going to move? It's with the exponent, it's with the x value, so it affects x. So it's going to go, it's a horizontal translation. Left 1. Okay? So basically, we're going to take that origin and move it left 1, and then we're going to regraph all the points. All right? So if I move it to the left 1, that's what I kind of like to think about. Does my horizontal asymptote move? No. Okay? My asymptote doesn't move at all because I didn't push the graph up or down anywhere. Okay? That's the only time that your asymptote's going to move. And so now I can just kind of regraph those same points that we had right there from that spot. 1, 2, 4. Okay? Be careful when you're graphing an exponential function. You never want it to actually hit the asymptote. Let it get close. All right? But don't let it hit it. Okay? What about the second one? What's the transformation on that one? It's 2 to the negative x if you can't see it. What does that do? It's a reflection. Which one does it go over? Y-axis. Okay, so it's a reflection over y. So does my asymptote move? Nope. Okay, it's still right here. We're just going to turn it the opposite direction. Okay.
Why is it y, but not x?
Because when that's going to affect your x values. So it's changing the x value. So I'd have -1, 2, yeah. That's why they pay me the big bucks. Okay. She asked why it was over y and not x. Because it's negating all the x values. When the negative's in the front, it negates all the y values. Negative changes the sign, negates. Okay? All right, let's look at this next one. He's kind of mean. All right? There's a lot going on there. Okay? This one's going to change my asymptote. How do we know? Yeah, there's a vertical translation, right? So we've got a vertical translation up 1. Okay? So that's going to move my asymptote. But I want us to look at what's happening with this part, that 3 to the 3x minus 3. Could I write that as 3 times x minus 1? Okay? Yeah, and I should. Okay? The reason I should do that is so that I can see the horizontal translation. Okay? How far am I translating it horizontally?
3.
Nope.
1.
1. My horizontal translation is just to the right 1. What does that 3 do?
It's a dilation.
It's a dilation, okay? It's a dilation. It's affecting x, so it's horizontal. So I have a horizontal dilation of how much? 1/3, okay? It's always a reciprocal. So this one we really messed with, okay? I'm going to move it around so that my asymptote's going to move. And then I'm going to change my original x values a little bit, okay? We're going to dilate it by 1/3. So that being said, let me just do some moving. Translation-wise, I want to go right 1. Vertically, I want to go up 1. All right? I like to mark that just so that I can see my asymptote, okay? I do that physical translation from the origin, all right? Now, if we think about our points that we have to graph, okay? Thinking about these originals, we're going to take those x values and divide them by 3, all right? So if I take 0 and divide it by 3, what would I still get? I still get 0. So my first point is still going to be 0, 1 up from that new place where I moved it. Yes, ma'am?
How do you know that the horizontal asymptote is?
Because I pushed that graph up. It has a +1 at the end, so that means I moved it up. So if I move it up, any vertical movement changes my asymptote. Because usually it sits at the origin, but that's not where I'm sitting anymore. Okay? Now, the next point, all right, on the original was 1, 2. Right? So I got to take that x value and cut it by 3. So that's going to actually be just 1/3 for my x value, but my y value would still be 2. And y'all, that's hard to graph, right? He's not going to move very much, all right?
Okay.
So from my other point, I go over just a smidge, but I still go up 2, all right? The next one, my x value is 2. I divide it by 3. That's 2/3. So I've gone almost 1, but I still go up how much? 4. Yep, I don't know what that extra dot was. I got too close. Okay, and so now we connect the dots. Okay, I do not think on the AP exam they will ask you to graph one, but I do feel they might ask you to explain the transformations on one. Okay, so understanding where all of that came from. Questions? That's the toughest one.
Okay.
All right.
Is this going to be on our test?
Yes. On the quiz, I don't know that I'll make you graph one, but I might ask you to explain about one. Yes, ma'am.
What are you using to, like, do it?
To get the points?
Yes.
I'm using these originals I got off of the original function up here, the parent function, 2 to the x. Those are points from that function, so that's what I'm using. Okay? Just like when you guys did your projects and you had your points and you translated them, same thing. Okay? It's the same thing. Okay. All right, and let's look at that last one. Oh. So y equals 1/2 to the x.
Horizontal dilation.
No, that would have to be next to x. All right, it changes the direction. It's actually the same picture as this one right here. Okay, think about it. That's just 1/2 to the x. I've not moved it anywhere. If you weren't sure what the points were, okay, I could plug in 0. 1/2 to the 0 is 1. Okay, 1/2 to the first is 1/2. I don't want to go to fractions, so I'm going to put a -1 in there. What's 1/2 to the -1? It's 2. We flip it over. All right. And 1/2 to the -2. It's exponent rules.
You lost me. Yep. You know.
Okay. 1/2 to the -1. Okay. Anything to a negative exponent does what? Flips. So this is just 2 to the first. Okay. So if I have 1/2 to the -2, that's 2 to the second, which is just 4. Okay. Properties of negative exponents. It is the exact same graph as we had in the second one. Okay. Just go in the opposite direction. Did my asymptote move? Nope. Okay. Properties of exponents. We're going to look back through some of them here in just a second. Right. So now that we've done a few, all right, just practicing some moving one exponential function, let's take one and then see if we can answer a bunch of questions about it. Okay. This would be on a non-calculator section, and Talon, this is more like probably what I would ask. Okay, one like this. So f of x equals 3 to the x minus 1 minus 4. First of all, what's your basic parent exponential function that we're moving around? 3 to the x. How do I know that? 3 is the base. Okay, so my parent is 3 to the x. If it helps you to get some points, get some points. All right, for just the parent. All right, what's 3 to the 0? 1. What's 3 to the, oh, I don't know why I put 3 there. What's 3 to the first? 3. And what's 3 to the second? 9. Okay, so I can get some points. I'm probably not going to graph a 9 if I'm just completely honest with you. I'm going to do those first two and curve that bad boy. Okay, because that's a lot of counting. All right. So now let's talk about the translation. Usually that sits right. I start at the origin and I graph those points. Okay. But let's just move the origin a little bit. All right. How does it want me to move this one? Translate it.
Right.
Right 1.
Up, down 4.
Down 4. Okay. So I'm going to take this 0, 0, this origin here in the middle, and I'm going to go right 1 and down 1, 2, 3, 4. Okay. Is my asymptote going to move? Good. Is my asymptote going to move? Yeah. I shifted it down 4 because it always is usually at wherever the 0 is, and I've pushed the 0 down 4. Okay. Now, from that little black mark that I made, that's my new origin, all I have to do is graph that table that's sitting right there. Okay? Not from the original origin, but from where I moved it. All right, so 0, up 1, right 1, up, I can't count, 3, and right 2, up 9. Don't let it hit your asymptote. Okay, so let's go through these questions over here because they're good ones. All right, what's my domain? Domain refers to my x values. All real numbers, okay? You can do this. You can do this. Or you can do this. Oh, I ran out of space. Hold on. Okay, I'll take any 3 of those representations, as will the AP exam. Okay, so the R with the extra line through it, ARN for all real numbers, okay, or negative infinity to positive infinity. Right? Let's talk about range. Those are your Y values. What Y values work for this?
Negative 4 to positive.
Negative 4 to positive infinity. Can it equal negative 4? No. Okay, this one's a little bit tricky. What would be the y-intercept? I didn't graph it here. All right, but let's think about it. Okay, if I did the y-interception, I'm thinking about these original ordered pairs. Okay, my first order pair was at 0. The y-intercept would occur at when x is negative 1. All right, because I go to the left 1. What's 3 to the negative 1? 1/3. Okay, so my y-intercept is going to be 0. All right. I'm only going to go up 1/3, but I'm down a little bit. So what's negative 1/3 plus 4? It's 4/3. Negative 4/3 or negative 3 and 1/3 works as well right there. We don't usually do mixed numbers. Okay. But that works. Okay. Where's my asymptote? Y equals negative 4. Okay. Is my function increasing or decreasing? It is increasing. Is it concave up or concave down? Up. And then let's do our 2 limits for our end behavior. Limit as x approaches negative infinity of f of x. And limit as x approaches positive infinity of f of x. Okay. On the left side of the graph, what are we getting close to? Negative 4. We're getting close to the asymptote. On the right side, what are we doing? We're going up forever, so positive infinity. Okay. Now, this, I'm probably not going to ask. All right, y-intercept. Okay. The other stuff is more important. All right. The other stuff is more important, especially the concavity, the increasing, decreasing, and the limit statements. Okay. That's what AP is going to be looking for. All right. Okay. Try this. Flip over the next slide. Try these at the top yourself. Okay. See if you can write those limit statements. A couple are pictures and one is not, so you're going to have to think about what it looks like. Okay?
Okay.
Try those 3. All right, let's see how we did. Okay? On the ones where they give me a picture, it's pretty simple. We just have to look at the graph. On the left-hand side, what are we approaching? 0. And on the right-hand side, positive infinity, okay? When we look at the second one, here's one that's been reflected and turned down for what, right? So on the limit as x approaches negative infinity, so sorry. To the left, all right, if you knew my husband, you would understand why I do that kind of stuff. It's just normal in our house. He's one of those people that makes up songs, 2 songs about things that are just going on. Anyway, okay. So on the left-hand side on B, what's it doing? Negative infinity. And on the right-hand side, 0. Now, C would be a non-calculator question. We have to think about what it looks like, okay? Is this exponential growth or exponential decay?
No, decay.
Decay. That middle is a fraction, so it's decay, so it's going to look like this. That should help me with the end behavior. So on the left, what's it approaching? Positive infinity. And on the right, 0. Okay? If it had a plus something or a minus something, that would be the number it would be approaching because my asymptote would move. But this one was not translated up or down. Okay?
So when you say that it has a plus or a minus something, that would be found in the x, right?
No, the y, because it would be outside of the exponent.
If it's found with the y, then it's left or right. It moves it left or right.
No, if it's with the x, it moves it left or right. If it's at the end, it moves it up or down.
Yeah, in the exponent. If
it's with the exponent, it moves it left and right.
Okay.
Okay.
And then
The 5 just makes it grow bigger, quicker. Yeah. It's just dilating it vertically, so it's going to be like super skinny. Okay. All right, so let's talk about a new irrational number. Okay. It's referred to as the natural base. It's called E. You can actually get to it on your calculator by hitting second and then LN. Natural logarithm. Okay. Euler is the guy who found this little guy. Okay. Euler. Good old ancient mathematician Euler. Okay. Ln is right next to 4. Okay. And above it, you should see e to the x. Okay. So it's an irrational number, and it's often used as a base to exponential equations. Okay. Now, it came from a series, all right, that was a sum, all right. And I guess you just had a lot of time. Here's where you guys had that factorial come up where you thought I'd put that in that problem the other day, right? And so it is the sum of the factorials, okay, 1 over the factorials to infinity. All right, I mean, they had a lot of time. All right, Euler had a lot of time. You've probably seen it in one of your compound interest formulas. If something is continuously compounded, P(e) to the RT, the PERT formula. All right, if you remember that from Algebra 2. But just like pi, there are digits that we typically remember for E. All right, now don't ask me why I have this in my headspace, but I do. Tolerate me for a minute. 2.71828 cha-cha-cha. 18, 28, 45, 90, 45, 23. Okay, so those are the first few digits of E that I have memorized because it was a song. Okay, anyway. We approximate E as 2.71 or 2.718. Okay, just like for pi, we use 3.14. For E, we use 2.71 typically. Okay. But it's just like pi. It goes on forever. Okay. So we're going to actually graph an e to the x function. You might be thinking, Miss Moore, how in the world do I graph a base of 2.7? We just kind of fudge it a little bit. All right? Yes, ma'am.
do we, will this be a calculator question?
With e, not necessarily. Okay, so let's talk about why it might not necessarily be a calculator question. All right, so let's take a look at this one. Let's just do a plain e to the x. Okay, and it wants me to graph it. Right, it wants me to graph it. So if we think about, that's not what I wanted. if we think about a table of points, okay, for just e to the x, so x and f of x. If we let x be 0, what's e to the 0? 1, okay? And if we let x be 1, e to the first is that 2.7. And y'all, that's all I'm going to fool with. Okay? I'm just not going to fool with it. We're going to approximate. All right? There's no reason to do anything different. Okay? So let's graph those points. 0, 1, and then 1, almost 3. All right? Now, did my asymptote move? No. Okay? It stayed right there at the origin. So let's just kind of walk back through the questions. Do we have growth or decay? Is E greater than 1 or between 0 and 1? It's greater, so it's growth. Okay? What's its domain? All real numbers. Okay? What's its range? 0 to positive infinity. We're not going to worry about that y-intercept, but what is it on this one? 1. Okay. What's my asymptote? Y equals 0. Does it increase or decrease? I don't know. It might have. Sometimes they flash. It's increasing, right? So decreasing is not applicable. It only does one thing. Where does it increase? The entire thing. Okay? So we can say all real numbers because it comes from the domain. Is it concave up or concave down? Up. All right? And let's do its end behavior. Limit as x approaches negative infinity. So what's it doing on the left? It's getting close to that asymptote, which is 0. And what's it doing on the right? It's going up forever, so infinity. Okay? So that's all stuff we can do without a calculator. All right? We have to think about what E means. E's just 2.7. Okay? So that being said, okay, yeah, I know. Here's one, all right, where they don't ask me to graph it, but they ask me all the questions. All right, Kelly Beth, you're my favorite. You're so expressive. Nobody's throwing up the finger yet, so I'm feeling good. Okay, don't do that. That would be rude. All right, here we go. So f of x equals e to the x plus 2 minus 1. I have to tell you, my least favorite professor in college was in my 3rd computer programming class. And God love her, she came in, she had the personality of a chair, all right? And she came in, and we had these massive whiteboards, okay? She never said hello, good afternoon, F you, nothing, all right? She just walked in and started writing, okay? And she never spoke, she just wrote. She'd fill up 2 boards, and when she got to the end of this board, sometimes she would pose a question. All right. Other times she'd go back to the first board, erase, go a little bit more, and then pose a question. All right. Well, none of us had any idea what she was talking about. Okay. And so we were all math teachers, and there were 3 computer science majors in the room. And they didn't even know what she was talking about. And then she would sit down and just look at the board until somebody answered. It was terrible. It was terrible. It was the worst experience of my life. So she had 1 office hour a week where you could go to her office and see her. Okay, if you got there 3 seconds early, she wouldn't open the door. The minute that hour was over, she kicked you out. Like, she was the most unfriendly person I had ever been around. All right, so I'm just saying, it could be a lot worse. Okay, here we go. But we got to where we would just giggle because we didn't even know where to start. You know, anyway, it's all good. I got a B. I didn't care. All right. In the end, you're just like, made it. Check. Okay. So here we go. Here's an E function. All right. Is this going to be exponential growth or exponential decay? Growth, because the base is 2. All right, so we know it's going to look something like this. Even if I don't know anything else, I know that. So is it increasing or decreasing? It's increasing. Okay, where is it increasing? Everywhere. All right, so all real numbers, negative infinity to positive infinity. All right. If it's increasing like that, is it concave up or concave down? It's concave up. Okay. The last thing we have to think about is our end behavior. And the only thing we have to consider with end behavior is where's the asymptote? Okay. So if we look at this one, where's our asymptote going to be? It's going to go down 1, that vertical translation. So my horizontal asymptote is going to be at y equals 1. Okay. So now we can discuss the limit, the end behavior. So the limit as x approaches negative infinity. Okay. If it's growth, what's it doing on the left side?
Going to negative.
It's going, that should be negative 1. Yeah, it's going to the asymptote. Okay. On the right-hand side, it's approaching positive infinity. Okay. So is that too terrible? And that is what I expect them to ask you on the AP exam. Okay. Just to give you something like that with all the translations in it, because that covers all standards from Unit 1. Then the exponential stuff, all right, with the increasing the concavity and the end behavior with the limits. Okay, so it hits both standards with one question. Okay, all right? Okay, better than we thought. All right, cool. Let's get into some algebra. This is my favorite part. Okay, we have calculus, and then you have algebra. But this is the best I got. Algebra. Okay. That's great. All right. So let's take a look at these properties of exponents. Okay. Properties of exponents. Just to review, okay, first time you hit these is about 6th grade, then you do them again, or maybe 7th grade, then you do them again, Algebra 1, and they come up again, Algebra 2, all right? So they're just always around, and things we have to think about. Product property, okay? If I had x to the 3rd and times x to the 5th, I would add those exponents to get x to the 8th, okay? That's the product property. If we're multiplying with the same base, we add the exponents. Right? Likewise, if we had x to the 3rd raised to the 5th, so the power property, all right, we're going to multiply those exponents, and so I get x to the 15th. And then if I have x to the negative 3, all right, negative exponent property, it's the witness relocation program. All right, you drop it to the denominator and you make it positive. All right, so that it's not negative anymore. All right. Now, here's what I want us to do for just a second. Look underneath. Let's investigate this for a second. Describe the transformation of this function. F of x equals 4 to the x plus 2. What's the transformation? Graphically, how would I move that graph? I would move it, I'd translate it horizontally to the left. Okay? I would translate it horizontally to the left, and I'd take it 2 places. Right? That's what I would do. It's a horizontal translation. But what I want to do is I want to take that expression, and I want to rewrite it using the properties of exponents. Okay? What am I doing to the exponents x and 2? What are we doing? I'm adding them together. Okay, and if I added them together in the to start, what did it become when I actually started that problem?
4 to the x and 4 to the.
Yeah, it was 4 to the x times 4 to the 2nd. Okay, so in order to have 2 exponents that were added together, I had to have taken that exponential base and I was multiplying it. Okay, Well, if I did that, could I simplify one of those? Yeah. 4 to the second is just what? So 16 times 4 to the x. Okay. What's the transformation on that rewritten function? It says that they're equivalent, but what kind of transformation do I have now? I have a dilation, okay? I have a vertical dilation. Of 16, okay? So we're saying that by the properties of exponents, a horizontal translation can become a vertical dilation, all right? It just can by the property of exponents, and that's one of the important things that we have to remember. That's part of the rewriting, okay? That horizontal translations can be rewritten as vertical dilations. Okay, so that was the big thing right there. All right, using those properties of exponents. Yes. Yeah. Got your iPad. Life's hard. Crap, that's a lot.
How would like we use this in exercise? Would it be like presented like graphically and like either?
No, I've got some multiple choice questions on here in a second. I'll show you. Yeah, it's probably going to be in a multiple choice question. Okay. All right, so let's take a look. All right, example 5. We want to rewrite these as their equivalent representation as a vertical dilation. So in other words, we want to take the addition out of the exponents. All right, let's do the first one together, and then I'll let you try the last two. Okay. So if we look at f of x, we started out by adding the exponents x and 3. So I would rewrite that as 2 to the x times 2 to the third. I know 2 to the third is 8, so I have 8 times 2 to the x. That's it. All right, try those last two. All right, let's look at this one, okay? It's subtraction, but that's the same thing as adding a what? A negative. So this is, oh, wrong color. This is 3 to the x times 3 to the negative 2. Okay. What do we know 3 to the negative 2 is? 1/9 times 3 to the x. Okay. Now the last one, there's an extra 4 there. Don't let that freak you out. Just keep it. Okay, 4. That would give me 3 to the x and 3 to the second. So if I simplify that, 3 to the second would be 9 times 4 is 36 times 3 to the x, okay? Yes, ma'am.
Okay, so on the last one right there, you put the x out.
Yes, it doesn't matter.
It doesn't matter if you put it in or out.
You could, yes.
Why don't you multiply them by the 4 first?
Because in exponential, in PEMDAS, exponents come before multiply.
Alright, I put my 3's in parentheses, but that's probably why I do it.
Yeah, okay. All right, so here's one more, all right, that I want to show you, this power of a property, or power property. Basically, we can do that by changing the base, all right? So if I had, for example, if I had f of x equals 4 to the 2x, that's the same thing as 4 to the second raised to the x. And my base is really just what? 16. Okay, so that's what that's saying. All right, so you can actually change the base, all right, in your exponential function. All right, so let's take a look at example 6. All right, this is what I expect on the AP exam. Okay, the kind of questions I expect. Which of the following functions is an equivalent form of the function y equals 9 to the 2x? All right. So if I'm looking at my options here, I've got 3 to the x, which I don't think I have going on there. I have 3 times 9 to the x. I have 18 to the x, and I have 81 to the x. All right. Well, if I look at what I started with, all right, 9 to the 2x, I could pop a parenthesis in there for 9 to the second and then my x. And how much is 9 to the second? 81. And so that's why this one would have to be D. All right, does that make sense? Okay, so that's what it's just properties of exponents. Okay, kind of a weird way to ask it, but properties of exponents. All right, and then let's try one more. Okay. So on this one, we're trying to get to 9 times 4 to the x. Okay, and when I look at my options here, there's a lot going on. All right. I've got 3 times 16 to the x over 2, 3, and then a 9 and a 9. My guess is it's going to be one of the bottom two. All right. Why do you think that's my guess as to where we would start?
Because you already have a 9.
Because I already have a 9. Okay. Because I already have a 9. So I'm going to focus on those two. That's just smart choosing in terms of my answers. All right. So now let's think about what those 16s mean. If I have 16 to the x over 2, that's the same thing as 16 to the 1/2 times x. Okay. 16 to the 2x is the same thing as 16 squared and then to the x. All right. So what is 16 to the 1/2?
4.
It's 4 because it's the square root of 16. Okay. So that equals 4 to the x. So there's my answer. Okay. 16 squared would be a big number. All right. So they're going to use a fraction there, all right, to test you on recognizing your roots, all right, with your fraction exponents. Okay. All right, so this is the one thing that I think will look a little different to you, something you've not seen, might be a little tougher to kind of work through. So it says exponential data doesn't always show a proportional change in outputs. Why is that? Well, sometimes our outputs have been moved vertically, all right? So just like we moved things up or down, all right, we added something, we subtracted something. What we're trying to do on these problems is to find the equation for f of x, all right? Or for g of x, or for h of x. Whatever y values are in the table, we're trying to find that equation without a calculator. I know, okay? So that's what makes it a little bit tough, all right? The reason they don't change is because of a vertical translation. We've either added 1 to the y values, we've subtracted 1, we've added 3, we've subtracted 3, like we've done something to move it up and down, okay? Now, I wish I could tell you there's some super mathematical way to go about this. There really isn't, all right? It's really kind of a guess and check, which is my least favorite mathematical method, all right? But I want us to look at this one, all right? I've got a 7, a 13, a 25, a 49, a 97. Those numbers mean absolutely nothing to me, okay? But if I add 1 or subtract 1, they become even. And maybe if they're even, there's some form of a 2 that goes with it. Either I'm multiplying by 2 or maybe multiplying by 4, something like that, okay? So I'm just going to think for a second. If I take it down 1, it's 6. If I take it up 1, it's 8, okay? If I take it down 1, it's 12. If I take it up 1, it's 14, all right? Do either one of those show you a possible pattern? The 6 and the 12, okay? I got lucky just taking it down 1 because I immediately see a pattern, okay? Let's see if it holds true. 25 minus 1, 24. 49 minus 1, 48. Y'all think we found it, okay? So simply a guess and check, all right? Well, what did I do? I took those y values and I subtracted 1, okay? I took the y values, f of x, and I subtracted 1. Now, let's write the equation for when I do that. Okay, what equation is left? Well, lucky for me, if you think your 0th term, I've got it right there. Okay, my first value is 6. What's my common ratio now? 2 to the x. Okay, so after I made the change, I wrote the equation for the change table. All right, but that's not what I want. I want to know what f of x is. How do I get f of x by itself in this equation? Add 1. And that's my equation. Okay, so that's a little weird. Okay, yep. I subtracted 1 to my y values. Okay, yep, where I got those new blue ones in my table. Okay. Let's work through the next one. Okay. So if I look at this one, I got 2, 10, 34. There's no multiplying or dividing that's working for those numbers, right? So my options, if I add 1 or subtract 1, that's going to give me odd numbers, and that's probably not what I want, okay? But we don't know, all right? So let's try adding 2, subtracting 2, all right? I really like the even numbers if I can make it happen, okay? So if I subtract 2, that gives me 0. If I add 2, that gives me 4. All right, so I'm just playing, all right, trying to keep it with even numbers. If I subtract 2 from 10, that gives me 8. If I add 2, it gives me 12. Notice anything? Yeah, which one shows a proportion there change, a multiply change? Okay, the adding 2, because 4 times what would give me 12? 3. All right, let's see if it works. 36. 108, 324, right? So, yep, that gives me a common ratio now of what? 3, okay? Gives me a common ratio of 3, all right? So, what did I do to my original y's, my g of x's? To get the ones I want, I added 2, right? Now let's write the equation based on those new blue values. What would be my starting value, my 0th term? 4. And what's my ratio? 3 to the x, but I want to get g of x by itself. So what would I do? Subtract 2. So it's a way for us to fit curves without using a calculator. Okay. Let's do one more, and then we're going to just look at some word problems that are super straightforward. They really are. Okay. Now, one of the things I think you should notice about h of x, what's happening to those h of x numbers? They're going down, all right, which means we're probably dividing by something, all right? So let's get it to even numbers. To get it to even numbers, we need to add 1 and subtract 1, all right? So I have 62 and I have 64. I have 30 and I have 32. Which one do you think is going to work? The 64, 32, where we're adding 1. So that's going to give me 16, 8, 4. That's the bingo. Okay. What's my common ratio now? 1/2. We're dividing by 2. All right. What did I do to the original h of x's to get the side I wanted? I added 1. Okay. And now let's write the exponential function. All right. What's my leading term right there? 64. My ratio is 1/2. And we're going to raise it to the x. Okay. To solve for h of x, what are we going to do? Subtract 1. So I have 64 times 1/2 to the x minus 1. You got it? Yay! Okay. I had to think through that for a hot minute. The guess and check really threw me for a loop when they introduced that to us. I was like, I don't like it. Because they didn't say that. They just said, go. I was like, I'm struggling to go.
Is that supposed to say -1/2? I'm not sure.
It's a 1/2. I just didn't complete my line. Thank you. Okay. All right. Last part, application. All right, application. Notice it has a little calculator symbol. Yay! Y'all don't love the calculator? Oh. Well, I'm going to teach you before it's all over. You'll know. Trial by fire. Okay, so between times 0 and 30 minutes, the number of fans inside a large sports stadium can be modeled by this exponential function. So they tell me it's exponential. Thank you. Appreciate you. Okay. Where F represents the number of fans inside the stadium and T represents minutes after the doors open. There are still 47 people in the stadium 2 minutes after the door opens. So I have 247. There are 2,602 fans inside the stadium 20 minutes after the door opens. Now, they didn't even pose a question, but here's what we want to know. Find F of T. Okay? We want to find F of T. We're going to use an exponential regression. They gave me 2 points. I'm going to let the calculator do it. All right? So we're going to do an exponential regression. Okay, so if I want to do a regression, where do we start?
Second count.
No, not yet. We got to put data in first.
Stat.
Stat edit. Okay, stat edit. Put your data in there. All right, we got X's, we got Y's.
When you do a stat, like graph thing, don't you have to put 3 points?
Only if it's quadratic.
Oh,
Yeah, if it's exponential, it'll do it with 2, which is nice. Okay,
but if we had to have 3, couldn't we use 0, 0?
not necessarily. Depends on the context of the question. Don't ever use 0, 0 unless it tells you. Okay? All right. Once we get the data in, then we go back to stat calc. And you're going to arrow down to choose EXP or EG.
Do we still store it?
Store it in Y1. Okay? We don't need it on this equation, but just get in that habit. Okay? We store it in Y1 with alpha trace. Okay? And then calculate. It's going to give you the value of A. It's going to give you the value of B. And so F of T. How many decimal places do we take? 3. Okay? Now, AP allows you to do 2 things. You can either round, all right? So follow the rules of rounding and round. Or it allows you to do what's called truncate, which means after the 3rd digit, just cut the bad boy off, all right? And that's legal, all right? It's called truncating, and so they let you do that. So 30.089 times 1 point. Now, this one was 2499, right? Yeah, 2498, something like that. You could do 1.250, or you can do 1.249. They would give you credit for both. Okay? I wrote down 250 to the x. All right? And there's your function.
That's all I have to do?
That's it. If it's a calculator question and they ask you to find an equation, find 2 points, use your regression. All right? Don't waste time. They want you to use your technology for that purpose. Okay? That being said, y'all try 10. Okay? This time it just gave me the table. Wasn't that kind? All right, you should have gotten 62.801. And I did 6.99 or 0.699 for B. How'd you do? Okay. I like those. All right. Let's look at 11. Okay. So it says the number of bacteria B in a particular culture can be modeled by this exponential function. It gives me an equation. All right. So B is the number of bacteria. T is measured in hours. So it says let A of T equal A times B to the T be an equivalent expression for B of T. Okay. So in other words, I want to write an equation that means the same thing, but looks a little different. Okay. Find the value of B. So let's just take a look at it. In other words, we want to change the base. So let's look at what we could do. Right. The 17 is not going to go anywhere. Right? But I could do e to the 0.31 and then a t. Right? That would be the same thing because they're both up there in the exponent being multiplied. All right? So if I do that, my base would become e to the 0.31. It's going to be a decimal approximation. You're not going to do anything fancy. You're just going to type it in on your calculator. All right? Second ln, so right next to 4, you put 0.31 in the exponent. Okay? That's all that question's asking. Worded extremely weird. All right? But that's really all it's asking you to do. All right? Is change that base because you've got two exponents up there that are being multiplied. All right? What is e to the 0.31? 4.3. Oh, okay. There you go. 1.363. And that's all it's asking you to do. Okay? So good question. All right. So now it says find the average rate of change of B of T over the interval from T equals 1 to T equals 7. Well, that's not a standard in this chapter, but we can do it because we've already learned average rate of change. Average rate of change says I'm going to find what? It's like the slope, right? Average rate of change is the slope. So we're going to use our B function. We're going to take B of 7 minus B of 1 over 7 minus 1. All right? Now, because this is a calculator question and I want to type as little as possible, all right, and it has multiple parts, I'm going to put B in Y1. Okay? I'm going to put that B equation in Y1. All right? And then I'm going to use my calculator so that I can pull up Y1 and put a 7 in parentheses. Minus, I can pull up a Y1 and put a 1 in parentheses. And divide it by 7. Just type it in. Go to Y equals.
Oh, okay.
Yeah. Just go to Y equals and type in your equation. Use X for T. All right. And then that way you can do it in one step. All right, which is nice. Alpha Y equals will get you the fraction, and you can make it look exactly like what I wrote down right there. Okay. So just to simplify the process a little bit. Okay, so now here's the answer I got, 20.952. Or I'm stopping, what?
Okay, so I'll put the thing in Y1.
Yes.
Now what do I do?
Okay, alpha Y equals to get a fraction. Okay, alpha trace to get Y1.
Okay.
And then parentheses 7. Close the parentheses, minus alpha trace, and do it again. Yeah. It's okay. Always stop me. Okay, but it's a rate of change in an application problem, which means we have units. All right. All right, let's think about our units. What are our units going to be on this? It's the rate of change. What are we talking about? Bacteria in hours. So what would my units be? Y's are on the top, so bacteria per X is on the bottom, hour. Okay, bacteria per hour. It's gonna, if that's a free response question, you don't put units, I guarantee you there's a unit point in there. Okay, so sometimes you can get 1 point just for getting the right units on there.
Alright, I get like kind of the Y one stuff.
Mm-hmm.
All that. How'd you get the 20.9?
I typed this in.
I know, but where do you go to get the answer for that? Would you do it in the Y one?
No, I put B of T in Y1. And then I typed that on the home screen.
How you put that in Y1?
Type it in.
How you get the, oh yeah, you get the E from the thing.
Take an L in.
Oh, wait, I didn't.
Oh, okay. I'm O N.
Okay.
20.899.
Well, I did it in a hurry this morning. I might have written it down wrong. Did you get what I got, Laura? Okay. And then on C, let's just talk about how to do it because we're going to run out of time. Find the number of bacteria predicted by the model after 15 hours. What would you do? Yep.
Y1.
Y1 of 15. Yep. Y1 of 15. And that would give you 177.945. And those are bacteria. Okay. All right, I want to do 12 really quick. We're just going to do A and C so that I can get you your practice because it's about time to go. All right. So I know we did 3 sections. The reason I'm doing one tomorrow is so that we can ask all the questions we need to ask tomorrow. All right, from the practice because we'll have some. So it says 50 deer were introduced into a large wooded area. It's an exponential function. The population increases by 13% per year. Okay. We want to write an expression for D of T. How many deer did we start with? 50. If it's growing by 13% each year, what's my base going to be? 1.13. It's 100% plus how much we're growing. Okay. So which of those values is A and which is B?
A is 50.
Yep. And 1.13 is the B. Okay. Now, that's in years. On part C, I'm going to just jump down there. Find an equivalent expression where T is measured in months instead of years. Okay. When we change the time, we change the exponent. All right. How many months are in a year? 12. So the only thing that happens to this equation is it's 50, 1.13 T divided by 12. Okay. You might also see it where they take that 1.13 and raise it to the 1/12th power and change the base. All right. That's possible too if it's multiple choice, but that would be an acceptable free response answer. Okay. All right. Let me give you your numbers to work on. On 2.3, there's just one worksheet for each. 2, 4, 5, 12, and 14. On 2.4, 2, 3, 5, 8, 9, 10, and 13. And on 2.5, 1, 3, 4, 6, 7, 9, and 10. Okay. Friday's lesson is all Algebra 2, by the way. It's composition of functions and inverses. So you should remember all of that for you. My Deca peeps are going to be gone. Okay. Tomorrow's going to look a little different. It'll be something you haven't quite seen. Okay.